Hi guys, so this time we're going to learn about the probability of union of compound events. So I highlighted the term union because aside from union, we also have a different operation involved compound events which we call intersection. So we'll dwell on intersection in the next video, but for now, let's focus in the union of compound events. But firstly, I want you to remember that when we say compound events, this involves two or more simple events. So yes, you heard it right. We will be observing here two or more simple events. Now the big question is, how do we determine if a certain problem involves union of compound events? Simply look at the clue word or, because or tells us that either. So that's the idea of union. So we simply combine the probability of the two events. Now there are two cases when we are combining or when we are getting the union of two events. Let's say event A and event B does not have any common result or any common outcome. So if we put or if we get their union, then we simply put them together. In formula, we express that as probability of A plus the probability of B. Whereas, the other case could be the event A and event B has something in common or an intersection. So what do we do in this case, since we are still getting the union or combining everything, the probability of A and B? So aside from adding the probability of A and B, we subtract the intersection, this one in the middle. So why do we do that? Simply because we don't want to double the count of the intersection. Because if we simply get the probability of A, then add it with the probability of B, then we double the count for the intersection, correct? That's the reason why we have minus here. Minus one copy of the intersection. That's the basis of our formula here. Now, what's the difference between these two? The first one is called mutually exclusive events. Again, these are the events or compound events which do not have anything in common when we are talking about the result. Whereas the other one is called sometimes mutually inclusive, or sometimes they are called non-mutually exclusive. Non-mutually exclusive events. And if you identify that the events has something in common or intersection, then we follow this formula. But if none, we simply do the addition of the probability of the two events. Now, to further understand the idea or the use of this formula, let's try to observe some examples. First example, a card is drawn from a standard deck. And we know in a standard deck, we have 52 cards. Question is, find the probability of drawing an ace or a face card. So here are the two events that we are observing. And again, the conjunction use is or, so we expect this to be probability of union of compound events. And since these are compound events in under union, so we need to know whether will there be a common result or outcome between A and B. So for A, event A, the possible results are, since it's an ace, so A of heart, A of diamond, A of clover, or it could also be A of spade. So these are the four possible results that we can get. Now for B, it's a face card, so it is all about the jack, queen, and king in their variant or different shapes like jack of hearts, jack of spades, and so on and so forth. Now observe, does the two set of events has something in common? Answer is none, so they are mutually exclusive events. If there are mutually exclusive events, then we follow the formula P of A plus P of B. Now assess what is the probability of getting an ace, since we denote it as our first event or event A. So event A is 4 out of 52 cards. Plus, for the face card, since we have Jack, Queen, King, and four shapes of each, so that's 3 times 4 copies, so that's 12 over 52. Since we're adding fraction here, I suggest do the simplification or lowest term at the end, so we can retain the similar fractions here and easily add 4 plus 12, that's 16 over 52. 16 over 52. And then here, we can simplify this as 4 over 13. So this will now be the probability of getting an ace or a face card. Now for the second example, still about standard deck of cards, but this time we are going to find the probability of drawing a heart or a 7. So let's say this is our first event, second event. So for the first event, just to observe if they are mutually exclusive or inclusive. In this event A, since it's a heart, so it could be a of heart, 2 of hearts, until King of hearts. Correct? So all the values of the same shape of hearts. So that's actually 13, a total of 13 from A to King. And for the second event, getting a 7, there are 4 possible. 4 possible are 7 of hearts, 7 of diamond, 7 of clubs, and then 7 of spades. Now, I'm doing this just for you to clearly see that there is an intersection between the two. And that could be 7 of hearts. So, showing we wrote also 7 of hearts here. So, that's common between the two. So, there's an intersection, therefore, they are non-mutually exclusive. So, we follow the formula, probability of A plus the probability of B, and then minus the probability of their intersection. So how do we represent this? For the probability of A, as I said, we have a total of 13 cards under hearts. So that's 13 out of 52 under standard deck. So 13 out of 52 plus probability of B, the only 4, since we have 4 copies of 7. So 4 over 52. And then minus the intersection, since there's only one common, so that's 1, which represents the 7, 1 out of 52. Chance to get a 7, which is the intersection. Now, doing the math, 13 plus 4, that is 17, minus 1 is 16. 16 over 52. In lowest term, this is 4 over 13. So, similar answer, but different type of question. And for our last question, this is composed of 4 different questions or different probabilities to solve. So let's do one at a time. A bag contains cards numbered from 1 to 14. Okay, so these are the numbers inside your bag. And then one card is drawn at random. Find the probability of, letter A, selecting a prime number or a multiple of 4. So again, it involves the operation or union of events. So we get the union of prime number. What are the prime numbers here? So let's list them down on top. Prime numbers could be 2, 3, 5, 7, 11, and 13. So you need to be careful on for the outcomes which are favorable to the event you are observing. That's very important. Now, on the second event, we are observing multiple of 4. So what are the multiple of 4 here? We have, of course, 4, 8, and 12. So we only have three outcomes. And observing these two, among their outcomes, there is no common result. So therefore, they are mutually exclusive. So we therefore conclude that these are mutually exclusive events. So we simply add the probability of these two. So the probability of the first event is probability of A plus probability of B. Let's just write it here so we are guided. Probability of A is 2, 4, 6, 6 out of 14 numbers. Probability of B, we only have 3 here, so that's 3 out of 14. Add them together, that's 9 out of 14. So this will be our final answer. Okay, now moving to the next question. For our next question, selecting a multiple of 2 or a multiple of 3. So again, among our sample space here, from 1 to 14, what are the multiples of 2 here? We have 2, 4, 6, 8, 10, 12, and 14. Whereas the multiple of 3 are 3, 6, 9, and 12. Better to list them down so you can carefully select or identify whether they are mutually exclusive or inclusive or non-mutually exclusive events. So here, they have 6 and 12 in common. So therefore, they are non-mutually exclusive events. If they are non-mutually exclusive events, then we do the formula, or we use the formula P of A plus P of B minus their intersection. So let's do that here. Probability of A, since there are 2, 4, 6, 7, 7 on the list, so 7 out of 14, plus probability of B, we have 4 on the list, the 3, 6, 9, and 12, so there are 4 out of 14. And then the intersection are 6 and 12, so the number will be 2. There are 2 outcomes favorable to the intersection, 2 out of 14. And doing the math, we have 7 plus 4, that's 11. 11 minus 2, that's 9. So again, same answer, 9 over 14. And for letter C, we have probability of selecting a 3 or 4. Again, it's a union. And obviously, this item here is mutually exclusive. Why? Because we are simply observing getting a 3 or a 4. So single digits to observe. And there's only one 3 and one 4 in the list. So nothing in common, therefore mutually exclusive events. If they're mutually exclusive events, then we have probability of A plus probability of B. And that gives us 1 over 14 plus 1 over 14, again because we only have 1 3 and 1 copy of 4. And we have 2 over 14 or 1 over 7 as our final answer. Now down to our last question, selecting an 8 or a number less than 8. So if this one includes 8, since it's exactly 8, and this one includes the number less than 8, so it could be 7, 6, 5, so on and so forth until 1. And obviously, they do not have something in common, so again, these are mutually exclusive events. If that's the case, so we then get the probability of A plus the probability of B. Probability of A is just 1 out of 14. The second probability is 7, 6, 5, 4, 3, 2, 1. Okay, that's a total of 7 out of 14. And that gives us 8. 1 plus 7 is 8, so 8 out of 14 or 4 out of 7 as the final probability. I hope those examples help you a lot in understanding how to get the probability of union of compound events. Now, to test your understanding, kindly answer this problem and don't forget to comment your answer for us to check.